printable concrete via innovative manufacturing paradigms. The speaker of the session will be Dr. Biranji Panda, Department of Mechanical Engineering, IIT Guwahati. About Dr. Biranji Panda, he is working as Assistant Professor in Department of Mechanical Engineering, IIT Guwahati. Before joining IIT Guwahati, Dr. Panda was a research associate in Singapore Center for 3D Printing and obtained his PhD in 3D concrete printings from Nanyang Technical University, Singapore. He is an associate editor of Journal of Materials in Civil Engineering, ACE, and received Research Excellence Award from Singapore for his contribution to digital construction. He has more than 40 journal publications under more than 3,400 Google Scholar citation with Hatch Index of 13. Dr. Panda's research focus on sustainable multifunctional composites and lies at the intersection of advanced manufacturing, material science, and multi-scale and multi-physics modeling. Examples of his current projects include additively manufactured sustainable composite, digital construction, and metamaterials. With this short intro, I request Dr. Biranji Panda to take over the section. Over to you, sir.
Yeah, good afternoon, Dr. Dinesh, and thanks for the invitation. So, can I share my screen now?
Yes, sir.
Okay, fine. Yeah, I hope it is visible, right?
Yes, sir, it's visible now.
Okay, fine. Yeah. Okay, so yeah, good afternoon, everyone. Thank you, Dr. Dinesh, again for the invitation. So today I'm going to talk about 3D printable concrete. It's a bit a different new topic because this technology of concrete printing, it evolved very fast in recent years. So I feel very privileged to work on this technology, and today I'm going to talk about the technological advance of this process and where we can adopt this technology for innovating the manufacturing, especially related to building and construction industry. So yeah, I'm Dr. Biranji Panda. I'm an assistant professor at IIT Guwahati. So basically, I'm a mechanical engineer, but still I have some interest in innovating the way we produce buildings through 3D printing process. So today, the content of my lecture will be something like the introduction to this digital concrete process, where I'm going to touch about more about concrete printing process. It is purely an extrusion-based manufacturing where we have to deal with very challenging requirements of rheology. So, which is going to be the second aspect of my talk. So here I am going to talk about rheology of the printable material, and then what are the materials that we need to fine tune for the extrusion of this printing process in terms of large scale printing, that also we are going to discuss. And thirdly, we will also discuss about the very common process parameters and how the process and property are related in concrete printing. So which is the third point. And finally, I am going to demonstrate some projects that already I have done and already we're planning to do at IIT Guwahati with the help of concrete printing process. So without delaying much, I'm just going into some digital construction technique. So what is digital construction? Nowadays, everywhere we are talking about Industry 4.0, talking about how the industry can be more digitalized. So in this regard, our construction industry also needs some innovation in terms of automation, digitalization. But if you see the traditional construction, which is more like a manual process, here the laborers, workers are trying to put their hands together to create a structure. If you see this process very carefully, you'll find that this process is more about a manual process where everything starting from creating the formwork. Okay, I think those who are from mechanical engineering, they could have imagined the situation very well, because normally when we do casting, we also create similar molds to pour the molten metal. So the same situation happens. Of course, in concrete, we don't do any melting. We move the fresh concrete in the box. The box, you can see this box is ready. Now these laborers or workers, they are trying to put their hands together to put all the fresh concrete in this mold box. So after a few days, when the concrete is hardens, these molds can be removed to finally get the structure. So this is how the traditional construction erects concrete structures. So what is the problem with this traditional construction process compared to other manufacturing or other industry? If you see, the productivity is quite stable over the years. So it is very important now that we have to also find some solution to automate the construction process to bring more digital technology to our construction process. So which really motivated me to take the help of 3D printing process to contribute in this domain. So as I mentioned, apart from this labor work, sometimes these people who are working in this construction, they are putting their life into risk, where sometimes they have to climb a very tall buildings to clean or to create the do any maintenance work. So these things, definitely we can try to find a technological solution where these problems can be minimized. So of course, the answer is not the 3D printing technology, but rather I will call it's a group of technology where we have to perfectly balance the combination of this technology for creating an automated solution for this industry. So yes, it's a very good question. Then what is the point of printing concrete? So I have two prime reasons for printing concrete. One is design freedom. So if you see the structure that is being put in my slide, it's a very complex structure. Okay, so if you see this process of printing the structure, we do not need any mold or the formwork that previously I have shown to you. So if you want to print a structure, we do not need any mold or the formwork. So directly we can print the structure directly from the 3D model. So the first advantage I have that I can print any design complex structures without the need of mold. So ultimately I'm going to save a lot of cost in terms of creating a mold box. The second reason, which is very appealing or close to my heart, is all about sustainability. So what is sustainability in terms of concrete printing? So there is an example of 3D printed concrete bridge in Netherlands. So what is the unique about this bridge? If you see the cross section, it is not entirely solid. Rather, the topology has been optimized to reduce the concrete waste. Okay, so what does it mean? That with the help of this 3D concrete printing technology, now we can optimize the material distribution because we have the design freedom. We can create some optimum design where we need less material. So in this way, you are also going to save a lot of material wastage that usually happens in traditional construction process. So sustainability and design freedom is the most critical point for me. But of course, since this is an automated solutions, we are going to have more advantage for automated systems. Like we don't have to work for 24/7. The labors don't have to be there. We have reduced manpower. The problems or the solutions will be more accurate. So these are some other advantages which is going to have if I'm going to use concrete printing process, because it is a technology driven machine which can directly print your structure from a CAD model. So this is an image of concrete printing process where a very complex structures can be printed by depositing the material layer by layer. So as I mentioned in my first slide, that this is almost similar to an extrusion based 3D printing process. If you are familiar with FDM process, where we deposit the molten plastic layer by layer, it is almost similar to this process, but the only difference you'll find that the layers are not hardened quickly for this process. So you can see this, all the layers that have been stacked together are very fresh layers. It means I can still put my hand and dig out some material from this process. It's a very fresh material. So we have to deposit a very fresh material in concrete printing process. So this is one aspect of printing process, but in some other solutions, we may have to rapidly harden the material to deposit more layers. So depending upon the requirements, we design the material so that the layers will be more stable. It won't deform. So this is one automated process can be applied to building and construction industry. There's another process which is known as D-shape. It's similar to particle bed fusion. So what happens here? You can see the video. So you can see it is a very big machine. So what is happening in this machine, that they're using sand. They're using sand as a powders, and we have a machine where this nozzle is carrying some binders. So these binders are being deposited as per your CAD geometry. So ultimately what is happening, from a stack of sand, we are selectively depositing this binder, and ultimately after the printing is completed, you can remove the loosened particles to get the final structure. So I think these two processes are very similar to extrusion based manufacturing and powder bed fusion. So it's a very big machine, but the powder is sand. So this is the nozzle, and this is the droplets. They are adding these binders over the sand particles to bind it together. And ultimately, you are going to create a very complex geometry. I hope in this video they will. So this kind of very lattice structures which is very complex in nature, you can fabricate using this machine. So the person you are seeing on my screen is he's a founder of this technology. So you can see you can create such a complex structures using the particle bed fusion. The advantage of this technology over extrusion based process is that here you can make more overhanging structures because you do not have to put about support material. But in case of extrusion based manufacturing, we have to provide the support material or we have to optimize the part geometry if we want to print overhanging structures. But in case of DSEP, as you have seen, that the sands are going to act like a support material, so you can print a more complex structure in a better way using the DSEP process. So apart from this, this is all about 3D printing process. But if I talk in general, what are the automated solutions that are still available in building and construction industry? One another process I would like to call smart dynamic casting. So what happens here if you want to create a column which is not cylindrical in nature? Regularly, if you see any beam or column, no, normally they have square or cylindrical shape. But suppose if I want to have in this architect shape, which is very difficult to create using casting. So for that reason, this group, they have developed this technology called smart dynamic casting. What happens, as you can see in the robot, they have an adaptable opening. So this opening is going to create a very complex geometry by twisting this complete nozzle. So during this casting process, this concrete is going to be erected and this opening is going to be variable in nature so that you can create this kind of very fine architect over the surface. So not only this kind of process, we have so many other robotic solutions that are currently being used in construction industry, like robot bricklaying machine, we have robot plastering. So a lot of automated solutions are being implemented in our construction industry. But in this talk, I am going to talk about more about 3D printing process, 3D printing of concrete. So this 3D printing of concrete is not a new topic, because if you see this video, which is almost like 80 years back, there was a process where they wanted to print a building by depositing the material layer by layer. But this material was not exactly cement, and the machine was also not similar to the machine that today we are using. But still, this concept was there 80 years back. I hope you can see the video that in this machine, they are trying to deposit this material layer by layer.
Person most of his time was devoted to the invention of equipment for the food industry. He's the author of the first building 3D printer. He created a prototype.
So yeah, as you can see, this machine was there to deposit the material layer by layer, and they also call 3D printing. So after 8 years, a news came that this machine can print the entire building in 24 hours. So if you see these two processes, the 8 years back technology and this one, so we'll find that today we have more advanced machine in terms of robotics, which is having more higher degree of freedom. So you can create more complex geometries. Even the materials also has been changed a lot, but the process is almost remain same. We have to deposit the material layer by layer. So this process actually started from a person called Professor Kushnabis, who patented the technology to print habitat for the person who are going to space travel. So if you are, the idea was like for the Mars mission, they wanted to create this small habitat for the astronauts. So this machine was initially patented by the Professor Kushnabis, who put a concept that using 3D printing process, we can create habitat in the Mars. And the process, if you see, it's a robotic system and it is depositing the material layer by layer. So after a few years of this technology innovation, then this technology get a lot of attention in Earth, because they wanted to create building structures using the similar processes. So if you can see the complete evolution of this technology, as I mentioned, this technology by Professor Kosnobis, he put this concept long back, but during a few years back, lot of companies, university, they have put lot of attention to improve this technology, because they feel that there is a really need of automated solution in construction industry. So you can see the graph is completely exponentially increasing, and in fact today a lot of companies are also doing these projects using this machine. So how the process works, as I mentioned, it is similar to your FDM process, where you have to deposit the layers by extruding the fresh concrete. So this is the nozzle, it is depositing the fresh concrete. We have a pump. So this pump is bringing all the materials down to the nozzle, and this nozzle is a 4-axis system because it is rotating during deposition, and we are using a rectangular nozzle to deposit the machine, to deposit the material. So this is a typical process of 3D printing of concrete. So you plan the design, and then you have a machine that is going to deposit it layer by layer, and we have a control system which is going to put a feedback that during deposition, if any failure happens, the machine automatically recode the whole system so that the deformation or the error can be compensated. So this is the machine which was used to deposit the material layer by layer. So as I mentioned, it is a 4-axis gantry printer. On the left hand side, you can see a controller. On the right hand side, there's a pump. So the job of this pump is to bring all the material to the nozzle, and this nozzle will listen the command from the controller, and it is going to deposit the material over the print bed. So like some FDM plastic printing process, the bed is not movable here. It is completely stationary, but the nozzle, the 3 axes, that is X, Y, Z, they can move according to the command by the controller. So this is one kind of concrete printing machine. It's not robotic type, but we call gantry type printer. But also I used a robotic concrete printer. As you can see, it's a big robotic arm. So the nozzle system remains same, means we have a connecting pipe. It's going to carry the material from the pump. And of course, if you program it, it's going to deposit the material layer by layer to get the complete structure. So let us discuss about what is the unique need of material for this process. If you see the concrete, it's a composite material. Those who are from mechanical engineering, I can say that you can assume that this concrete is a composite for you. It is a mixture of sand, cement, water, and stone. But in concrete printing, we are not currently using the stones, rather we are using these fine sands. So cement, sand, water, and some admixtures currently we are using in concrete printing process. So if you see the process very carefully, it is very clear that we have to first pump the material to the nozzle. So during this pumping process, the material have to be very flowable. Otherwise, it is very difficult to pump such kind of concrete to the nozzle. So if you want to create a pumpable mix, it means the viscosity of the material should be as low as possible. So it means the viscosity should be low. But if you're going to use the low viscosity material, once you deposit, because of low viscosity, it is going to spread away easily on the print board. So this is not again required in our concrete printing application, because we always want the material to remain in the same shape of nozzle. Suppose we are using a square nozzle or cylindrical nozzle, the filament that we are depositing in the print bed, it should retain its shape as it is. If it is flowing away or spreading away, it means the material design is very poorly designed, or it's a very bad material for concrete printing. But if I see the need of my pumping process, I have to create a very flowable mix. But if I simply deposit this flowable mix, it is going to be flow away on the print bed. So neither I need this kind of material, nor I need a very stiff material. Because if I have a stiff material, I have to apply very high pressure for pumping. And once I deposit, this layers will be not continuous, rather it will be discontinuous in nature. So this is the problem with high viscosity material. So now let us talk about how we can improve this process. So to improve this process, it means that we need to maintain a minimum yield stress so that this material should not flow away, nor it should be discontinuous during printing. So we need a minimum yield stress for pumping, and also the same yield stress is going to be responsible for holding the shape as per the nozzle. But if the yield stress is very high, then what is going to happen? We are going to have an issue of poor bonding risk. And if the yield stress is very low, then after printing up 2 or 3 layers, it is going to collapse like as shown in this picture. So we need a minimum yield stress. So if the yield stress is very low, then after printing a few layers, it is going to collapse. If it is too high, then we are going to have a very poor interlayer bond strength. So what is going to happen if you are going to do the bond test? You will get a very poor interface bond strength. So it means we need a minimum yield stress for printing, and with time the yield stress have to be increased. Otherwise, you cannot deposit more layers. So now again, we are coming back to the same concept like FDM, where the material have to be hardened with time, because now I want to deposit more layers. More layers means I want to have a structure which is beyond 2 or 3 meter height, so that I have to deposit more layers. And in this regard, the material yield stress have to be changed with time, changing in terms of increasing with time, so that it won't collapse during the printing. So this is the key mechanism of designing material for concrete printing application. So we also use the concept of texturotropy. So what is texturotropy? So it is a scientific, it's a phenomena of fluid flow. So if you know this example, that early morning, like when you press this tube, the paste comes out of the tube very easily. Okay, you don't have to press very hard to get out of this paste. So we need a very less pressure, but you see that once you deposit the material in the brush, it remains in its own position. It neither spreads away or it's not very difficult to squeeze it out. So it means this material is having texturotropic property. What is texturotropy? It means once you apply high shear rate, the material should easily come out of the nozzle, but as soon as you remove the force, or as soon as you stop pressing the tube, it should remain in its original position. Okay, so that is the unique feature of the texturotropy, and similar material property we need in concrete printing process. So as I mentioned here, that the minimum yield stress is something around 1000 Pascal. So if you're maintaining this kind of yield stress, we can deposit the layer smoothly without any deformation. So can we get this yield stress if we are going to use cement, which is very commonly used in construction process? Yes, it is possible, because cement grains, if you look into the mechanism, what happens? This is the mechanism that is explained with respect to time. So what happens once you add water to cement particles? They try to flocculate. They try to come together because they have a van der Waals force of attractions. And also with time, the CSS particles get formed, and they also try to bind the two cement particles. So in this way, with time, the cement particles try to flocculate. They have a van der Waals force of attraction. And because of this force of attraction, once you stop applying any force on the material, it remains in its own position. And now if you want to destroy it, you have to apply some shear rate. So these bonds are very weak bonds which can be easily destroyed. So it means this bond is really useful for concrete printing process, because it is not so strong that you have to apply high pressure to break it, but this bond strength is enough to create this yield stress, so that the layers will remain stable after printing. So this is possible using Portland cement, which is commonly used in building and construction application. But suppose, as you know, the cement, it is not a good material, because during the production, it creates a lot of CO2 emission, and also the process of cement production is an energy intensive process. It needs a lot of energy to create cement. And for that reason, to maintain environment friendly material, what we have done, we have collected some industry waste and try to replace it with the cement. So if you see this industry waste, it is spherical in nature. So this is just a waste of an power plant industry, and we wanted to replace the cement with this industrial waste. We then thought that we can create more sustainable mix design for this application. So what happens, that when we replace the cement with such kind of particle which is spherical in nature, they can easily flow away. So ultimately the yield stress becoming very low. So ultimately, if I deposit more layers, it is going to collapse after printing a few layers. Okay, if you see the structure, that it is completely collapsed after printing a few layers. So we still wanted to use this industry waste in our mix design, because our goal was to create sustainable mix. And for that reason, we try to investigate what else we can do to improve the buildability. We call buildability. How many layers you can deposit, we call buildability. So we wanted to improve the buildability of this material, and for that we use some nano clay. This nano clay, it really helped in improving the yield stress. As you can see, with 0% dosage, the strength, the yield stress is very low, but when the dosage increase up to 0.5%, the yield stress significantly increased. And if you look into the mechanism, how the clay is affecting the process, we found that a flocculation in the process which is again improving the yield stress of this waste replaced material. So how clay affects the rheology? So there are several concepts that have been demonstrated in the literature, but especially in the case that we are printing concrete, we found the flocculation of the clay is very important, and which is improving the yield stress to a significant value, so that I can put now more layers without any deformation. And as you can see, more layers have been added now without any deformation. So it is the clay that increase the flocculation, and result of that we can deposit more layers without any structural collapse. Sometimes what happens, since these materials are very fresh, then the deformation happens. So to avoid the deformation, we added some distance sensor, which is continuously going to monitor the distance from the top. So if there is any deformation during the process, we will get a feedback, and accordingly the process parameter will be adjusted so that the deformation can be minimized. So this is how we have also improved the process to minimize the deformation during the process. So now suppose when you have the texturotropy behavior in the material, it is very important to characterize the texturotropy. Otherwise, we cannot create new mix design. So to characterize the texturotropy, we use a rheometer which was available in our lab. So we did two testing. One is shear thinning testing. One is viscosity recovery to measure the texturotropy of our material. So what happens in shear thinning process? We take a bulk of material, we applied high shear rate to see what is happening to the shear stress if you apply high shear rate. So the material we printed, so we can see that once you apply high shear rate, the shear stress coming down to very low value. It means it gives a factor of lambda, which is around 0.41. It says that the material is very good for concrete printing application, because as soon as you apply high shear rate, the viscosity or the shear stress goes down to a very low value. If this value is not low, this equivalent value is not low, it means that even after applying some high shear rate, the material is not completely destroying. The shear thinning behavior is not promised for your material. So this is how we characterize the shear thinning behavior, which says that during pumping, what is the effect of pressure on the material. So if this breakdown is more, it means we can easily pump the material without any problem. So it's all about characterizing the pumping process through shear thinning protocol. So now once you deposit the material, it is very important to measure viscosity recovery. So what is viscosity recovery? It is very clear that during pumping, we need a very low yield stress material or low viscosity material. But the same viscosity cannot be there once you deposit the material on the print bed, because it's very low viscosity, the material will simply flow away. So we want the material to recover its original viscosity. What is original viscosity? It means before you pump the material, what was its viscosity at rest. So you mix the material, you put it on a chamber, and you measure the viscosity. But now during pumping, because of high shear rate, the viscosity went down to so low value. But after you deposit this material on the print bed, this material should have the capability to recover its original viscosity, or else it is simply going to spread away after you deposit on the bed. So you can see the material that we printed, it has the ability to recover almost 80 to 90% of its original viscosity, which is really good, because this higher viscosity on the print board is going to help for maintaining the shape of the filament according to the nozzle shape. So this is how we always characterize new materials to fine tune the mix for concrete printing application. So as you can see, sometimes we can print more layers without any deformation. So 60 layers have been printed without any collapsing or any deformation, because the material was designed in such a way that exactly at 60 minutes, because normally we assume that if you can print one layer in 1 minute, so 60 layers you assume you can print in 60 minutes. So the material will get stronger with time, so that once you deposit the top layers, the bottom layers will also harden, and as a result, the structure is not going to collapse at all. So this was the initial development of using a waste material for concrete printing application. Then we also worked for a competition that was organized by NASA. So as I previously told you, the key concept was to create habitat for the astronauts. So they put an advertisement that we are going to have a competition where you have to print concrete structures, but the challenge was you don't have to use water. So as you know that in concrete always we add water to mix the material, but so for this competition we developed a new material which required very less water, as the competition targets to use the minimum amount of water. So we developed another polymer known as geopolymer for this application. So you can see, as they mentioned in the competition, we have to use an automated system. So we had a small robot in the laboratory. We just converted it into a printing process, and you can see that with our newly developed geopolymer material, we were able to print some structures for them. So it's a very simple machine. The robot is connected with a pump, and this pump is depositing the material directly to the extruder, and as per the CAD model, these materials are being deposited layer by layer. Yeah, so if you investigate the material mix design, actually it contains again the same waste material like fly ash, slag, and instead of water we use an activator which is potassium silicate solution. So if you see the solution, it has higher viscosity than the water, and it depends upon again the concentration of the activator. So if we are using an 1.8 molar ratio or activator concentration, then its viscosity is slightly higher than the water. And if you're going for using 2 molar ratio activator, its viscosity is again higher. So ultimately what is happening here, that according to the viscosity of this activator, we are going to end up with a material which is higher or lower viscosity. And as you know, in this concrete printing, we have to carefully control the viscosity of the mix. So it is important again to find the suitable activator for your application. So as you can see that what is happening here, that different activator and different molar ratio, they are creating the mix with different yield stress and viscosity, because the activator is playing a critical role in controlling the viscosity of the final mix. So you want to try different mix design, and if you want to investigate, of course, it is very true that when you are having a concentration of 2.0, which is creating higher viscosity, you will expect a material which is having more safe retention compared to the material which is 1.8 activator concentration. So it means, so if you're trying to develop new mix design, it is very important to know what are the critical components that are affecting your viscosity. And if you know the viscosity that is needed for your application, definitely you can control the mix design to have a controlled filament as it is shown in this picture. So of course, if you want to add more layers, sometimes depending upon the material yield stress, the deformation will grow. But what we have seen that when you want to print a very poor material, after printing a few layers, this deformation height is going to increase. So we call stand-up distance. So as you can see, with more addition of other layers, this distance will keep on increasing. But if the material is not deforming at all, it means all the layers are stable. You won't able to find any deformation height in between the tip of the nozzle to the top layer. So this is how the materials are always being characterized for a final print. So you may go either for rheological test. Sometimes students, they try to do some kind of test to find whether the material is slumping. In civil science, we call slumping behavior. So if the material is slumping during the printing process, you will get this kind of stand-up distance increasing. But if there is no slumping, material is very steep, accurately it is being deposited, you won't find any significant difference from here. So this is how two materials behave completely differently from concrete printing point of view. So with the eval of this printing process, we are able to print 60 or more than 80 layers without any deformation. Also, we try to print some overhanging structures to explore what is the possibility of printing complex geometries, because in 3D printing it is better to explore more complex shapes which cannot be casted, and ultimately we are able to print this new material without any issue of collapsing. But the point is, now if you want to do the same thing for the previous mix design, we have to do some modification at the nozzle, because to control the material buildability, we have to find some solution so that once you deposit the material, it is quickly going to get hardened. So there are different solutions you can adopt at the nozzle here, so that the material can be hardened. There are some solutions where people are using microwave at the nozzle to immediately cure the concrete so that you can deposit more layer. There are some solutions where they're trying to add some chemical so that this material going to be quickly hardened after it being deposited. So there are many solutions to increase the hardening rate of the concrete that is being deposited, so that you can put more layers. So if you want to go with the second approach, that you have to add some chemicals which is going to increase the setting time of concrete. Setting time means the time that is needed to get hardened. So if you want to play with the setting time of concrete, and in this way you want to add more chemicals, so we have to come up with such nozzle design concept where one inlet will be used for material, another inlet will be used to get the chemical, and these two will be get mixed and deposited layer by layer, so that once you deposit the material, it will immediately get hardened, and as a result of that you can print more layers without any deformation. And this complete things has been depicted in the picture, that with time, if you want to print higher or tall structure, the yield stress have to be go exponentially high. And this can be possible, as I mentioned, by adding the chemical or by adding some microwave heating, which is can cure the concrete at a very higher, faster rate. So apart from this test, we also developed some new tests where you can see the green strength, because you are loading the fresh material layer by layer. So it is very important to know how many layers you can deposit. So if you see this material that is being deposited, it is experiencing a compressive force from the top layers. So we conducted the green strength test to measure what is the load bearing capacity of this material. So at different time interval, we conducted the test. So which is most important in concrete printing, that because you are printing a large structure, so maybe the first layer will be deposited at 5 minutes, but the last layer will be deposited at 150 minutes. So the material behavior will change, because concrete will harden with time. So it is very important to know how your material behaves at different time interval. So to get more knowledge about the green strength, we conducted this test where we compress the material at a different interval of time to know what is the load bearing capacity. And we got this load versus deformation graph, and using this graph and another test which is known as shear test. This shear test is used to find the shear property of the material. So compressive property and shear property is combined together to do a modeling, so that now we can at least predict how many layers we can deposit before the complete structure get collapsed. Okay, so this collaboration we have done with RMIT University Australia. So they have used the experimental data to model the entire printing process. I hope you can see that they are trying to deposit the layer virtually, and they are seeing that what is the maximum stress that is occurring on the bottom layer. So this model, it incorporates the time dependent property of the material, so that if the material is hardening with a very fast rate, you won't see any stress on the bottom layer. So depending upon the height, the structure you are printing, this stress has been simulated in this model, so that we can predict the number of layers we can print. And it has been compared with the experiment. You can see 6 layer depositing, here also 6 layer. So when you are going towards end, it's going to collapse because of higher stress. So bulging effect you can see. So why it is important? No, like because sometimes we want to print a very tall structure, so we can't directly go on a trial and error basis because it's a very large structure. If it fails in between, it's a very difficult task to clean all the materials and reprint. So it is always better with our experience and with material data, we can always do this buildability model so that you can predict at which layer it is going to collapse. So what we do, we are going to stop the machine and again take a break to print more layers, because by the time the material yield stress will be improved, so that addition of more layer is not going to disturb the structure. So this is all about how you deal with material. But in other 3D printing, like we also deal with process parameter design. Similarly, in concrete printing also, the process parameter design are important. So for example, if you want to print the material with different speed, it is very clear that without changing the flow rate, if you are changing the print speed, if you are going faster, the filament width is going to be get smaller. And if you're going very slowly, material will be getting deposited more, so the width of the filament is going to be more. So always we have to deal with this kind of problem. So before we do printing, we have to optimize the relationship between the flow rate and printing speed. This have to be combined together, otherwise the filaments will look very ugly. Either it will be over deposition of material, or sometimes the filament will be very smaller. So this is how we deal with the printing speed and flow rate. Sometimes also, depending upon the nozzle shape, we also get different properties. For example, if you're going to use a cylindrical, like circular nozzle, you're going to end up with this kind of porosity. But now if I have a square nozzle, where I can have a more compact structures. So again, one more point I would like to highlight here, that in concrete printing, only the nozzle shape is not an important point, rather the material is also important. Because whatever picture you are seeing here, it is this material is very stiff material. So you can see even after printing, it remains its shape exactly same as the nozzle diameter. But now imagine this material you are printing is slightly slumpy material. So what is going to happen? This cylinder is going to turn into ellipse. Okay, and so as a result of which you are going to get less pore in the structure. So what is key point here, that in concrete printing, it is not only about the material, but also the process parameter is going to affect the final print quality of the structure. So if I am using a very stiff material and my nozzle is circular nozzle, so the layers will be exactly as shape of my nozzle, and we are going to get more porosity. But now the same nozzle can be used with a very slumpy material which is going to deform after printing. So ultimately it is going to minimize the pore. And instead of that, if I'm simply straightforward printing the whole structure with a square or rectangular nozzle with a higher overlapping, so this porosity can be further minimized. So now let us talk about design. Why design is important? So to do some design experiment, we printed a toilet unit. So you can see this is a 1.8 meter tall toilet unit, and we have designed it. And during printing, what we observe, that sometimes we have this kind of very cornering issue. So we call cornering issue because here we have a sharp radius of curvature. So we have found that during printing of this radius of curvature, we get some layer tearing on the outer periphery of these layers. So you can see these tearings happens, and we investigated that it happens of many reasons. Suppose you are printing with a very stiff material, you can always expect this kind of tearing of surface. But now, even you don't want to change the material, you want to avoid this tearing, the only solution is that you have to improve the radius of curvature. But from design perspective, if you don't want to do that, what is the other solution? You have to make the material slightly more slumpy, so that even this sudden change in the radius of curvature or sharp turn, it is not going to affect, because your material is now a bit slumpy. It's not stiff. The stiff material turning very fast, less radius of curvature, you are going to end up with such kind of scenario. But if you keep increasing it, of course, you are going to minimize this defect. But at the same time, there are some other solutions, like as I mentioned, your material can be slightly soft, and you can also go slowly during this turning. So there are many aspects that is finally controlling the quality of your printed object. So now let us discuss about the strength. Normally in casting, we have one strength, but in concrete printing or in other 3D printing process, we have anisotropic property. It means that in different direction, we get different strength. Same happens for concrete printing. So to prove that, what we have done, we have printed a block and then we have extracted these blocks out of this big cube. Okay, and then we applied force in different direction, F1, F2, F3. You can see these layers are oriented in different direction. We applied force in different direction and we wanted to see whether this concrete is going to have same property in all the direction or a different property. So we found that for compression loading, F1, F2, F3, though F1 is having a higher strength, but if you see the difference between F1, F2 and F3, it is still acceptable in building and construction industry, but it is slightly higher than the casted one. Okay, why it happens? Because if you're printing in F1 direction, that the material is going to be more compacted in the direction, so of course you will get more strength. But which is most interesting is all about when you are going to conduct 3-point bending test, because here these two directions are very critical. In F1 direction, if you want to apply force, so which is going to be very less, because in this sample the bond strength between this layer was very poor. So if you want to do this 3-point bending test in F1 direction, we ended up with a very low bending strength, but in F2 we got highest strength. And when we discuss about the poor bending performance in F1 direction, we found that here an interesting phenomena happens, which is the bond strength. If the bond strength can be improved, the strength in F1 direction can be improved. Then what we did, we started investigating the bond strength, and for that reason we printed 2 layers of concrete with different time interval, because as we know the concrete hardens with time. So with different time interval we printed these 2 layers and did the bond test, and we found that this bond strength is the function of material, time gap and process parameter. Let me explain this to you. So what happens, suppose if the material is hardening very fast, in that sense, even if a gap of 5 minutes between these 2 layers is going to create a very poor bond strength. But if the material is very sleepy material, the material is not hardening immediately, even if you can delay 5 to 10 minutes, you will still get acceptable bond strength. So how fast your material is hardening and what is the time gap, these two are highly dependent and it is affecting your bond strength. What about process parameter? So we have found that during printing, if you are printing with a very slumpy material and squeeze it, squeeze means you have to press the layer. So in technical language, what we mean by pressing a layer, that we decrease the layer height. So when we decrease the layer height, and if the material is very fresh and slumpy in nature, means it has very fluidic nature, then this porosity in between the layers can be minimized. So the same thing is not going to happen if you are having a stiff material, because the stiff material, even if you press during the printing, there will be some voids which cannot be avoided. And if this material is fresh, then this void can be avoided. As you can see that even if you print with a higher lower this layer height, this porosity can be minimized, and of course the reduction of porosity is going to improve the bond strength. So with this knowledge of material design, process parameter and how you design the structure, we conducted a few projects. As I mentioned, our first project was to do a demonstration of toilet printing. So it was almost like 2-meter tall toilet unit. So we printed this, and that time our Prime Minister, he visited our university. So we also demonstrated the technology. He appreciated that, okay, within very short span of time, the whole structure can be printed. And of course, there are some problems which can be definitely solved in future printing. But he really appreciated that this is how we have to print the structure or more complex, which do not record any mold. So without the need of mold, you simply design the structure, press the button, it's going to print the entire structure for you. And the next project was all about printing a complete bathroom unit. So it was almost like 3.2 meter tall height. So for that, since the gantry printer was not sufficient, we used the robotic printing system to print the entire bathroom unit. The bottom part was casted, the layers or the walls was printed with lattice structures. So we preferred lattice structures because it is going to make the wall more lightweight. So I hope there's a video, you can see the complete printing process. See the pump, it is going to push all the materials. Yeah, I think I'm running out of time. So you can see after printing, we tested the structure. You can see after printing, we did some large scale testing of the structure. So to make sure that concrete printed structures are not weak. And we successfully passed the test. And now in the industry, they are trying to implement the structure in a building. So yeah, some advanced work has also been done to put reinforcement. I think I'm running out of time. So I'll just quickly just tell you the story that also to incorporate reinforcement, we have developed some nozzle where this reinforcement can be also added during the printing process. And addition of this reinforcement is going to improve the load bearing capacity of the material. So we also did some tests on printing the curved bed because to create more architect stuff, we have to print in different print bed. So this is a very it's non-planar print bed. So using this robotic platform, so we printed the concrete over this non-planar surface. So what is the application of such structures? We wanted to create a facade elements for building. And sometimes when a small robot cannot do your job, we have to take the help of multiple robots. So you can see in the video that two robots is printing a large structures combinedly without any collision. The complete structure is printed by just two robots. So multi-robot printing is important. And just I want to conclude my talk with some examples like what has been done in the world. There is a company called Cybe. It's creating a lot of structures, building in Netherlands, and some company like X3, they are more clear about how they want to design this nozzle to print more complex structures. So if you see, this is very difficult to create using casting process. But with the robotic system or 3D printing, you can directly design the structure and print it without the need of any mold. So recently they have printed some rainwater harvesting unit because they feel it's more lightweight compared to the casting. It takes some time. And this company, they're also more into more architect structure printing. This can be done through this printing process because you have the design, and if you properly design the material that can be strong enough to support more layers, of course you can print those complex structures. So they're creating some furnitures. This is the company I already told you in the first 2-3 slides. They have printed the entire unit in just 24 hours. And now the same company using a crane type robotic system, they are printing the buildings in Dubai. So as you can see, the walls are now no longer brick and mortar walls. Rather, it is a lattice walls, and it's going to be more lightweight. And this lattice wall now can be used to hold some kind of pipings, electricity connections. This is the entire 3D printed buildings. In China also, they had already printed some buildings. They are printing the walls and assembling it on site to create the whole building. So at IIT Guwahati also, we have a 3D printer. We have recently started the group, and we wanted to create more design of material mix, and also we want to improve the machine in terms of automation, bringing more inline monitoring systems so that the printing process can be more advanced. So with this, I would like to thank the organizer. I hope there are a lot of important key takeaways, like the material machine parameters, designs are important, reinforcement, structural integrity, cost, all these things are very important. It's slowly being addressed by the research community. Hopefully we can do some good work in this topic. Yeah, thank you very much. I would like to thank all the sponsors, my university, IIT Guwahati, for allowing me to continue this work. Thank you very much. If you have any question, I'll be happy to answer it. Thanks again.
Thank you, sir. Thank you very much for the wonderful session, because every child is an innovator. His innovation or our innovation start with building a sand house. That's how all we start with the childhood. Now we are very happy to visualize like there is something which is completely organized by 3D printing going on with steps, and the world is moving towards completely on that too in 3D printing. It is creating a lot more technology. Participants, what are the doubts you have? You can just raise up. There is a